Ladies and gentlemen, welcome to video number 22 in a series of video lectures that are companions to the book The Fivefold Sun, which was filed at the Bibliothèque Nationale de France in Paris in late 2017. We are today, December the 4th, in the year 2018, about a year later. Today we shall discuss in part 5 of this book, chapter 5 of the second section, which is devoted to the toroidal period doubling sequence of solar oscillations with a length of more than 15 years. You see here a table on which the component periods which compose this suggested sequence are put together, starting here with the Hale cycle estimated at 21.6 years, ending with a period of 707 years, which is also found as a sharply determined oscillation length in the spectral data that were introduced in the previous video together with the methodology to arrive at the detection of such peaks. What is interested in this set of period lengths is that they approach integral multiples of the length of the Schwabe length, the multiples being powers of 2. In other words, this is a period doubling sequence in which you see the first doubling 2 Schwabe cycles. The Hale solar magnetic cycle is very close in our estimate of the theoretical value of exactly 2 Schwabe cycles. Also for the 8 Schwabe cycle length. But what is more surprising and interesting is that the 2 longest detected periods in this sequence are also extremely sharply defined. You see plus or minus only less than 1% versus the theoretical value defined by a multiple of the Schwabe length, which is a power of 2. These are the contents of this chapter, chapter 5 and section 2. We called in the book this sequence the first peak sequence, the one for which we have the strongest evidence. And it is composed of the shown 6 consecutive powers of 2 as the integral multiples of the Schwabe cycle. Of course, they are only approached, but as just said in several cases, they are on the dot. The 353-year period, the 707-year period, for example. You see in orange color, the expected period lengths are in general rather close to the estimated length empirically from observations as in the present chapter. So after all, why the fuss? Why spend over 1 year of research to merely confirm a phenomenon of almost exact period doubling? Is there no additional useful information in these findings? One of the new pieces of information that we gather from the present investigation is in fact that we find among the several fluctuations that are detected in this sequence of period doubling fluctuations, there are 2 powers of 4 which are not powers of 8, and the integral number of Schwabe cycles that they represent. This is the 45-year period of about 4 Schwabe cycles, and the 168 detected period of about 16 Schwabe cycles. The shared characteristic in terms of a spectral analysis for these two oscillations is that their peaks are very smeared compared to the others. There is, as you can see, an error bar of about 7% in both cases, plus or minus 3.5 years and plus or minus 12 years, which is much larger than in the other cases. And for the two longer periods, as just said, we have instead very sharp peaks. In terms of phenomenology, as we shall see, these two periods for which the integral multiple is a power of 4 and is not a power of 8, may apparently correspond to some solar activity anomaly, or at least a sort of a solar excursion. So those are the, again, powers of 4 and not powers of 8 as integral multiples of the Schwabe length, the smeared peaks, which maybe correspond to solar excursions and solar activity behavior. For the 4 Schwabe cycle periodicity, there is weak evidence. In fact, it is one of the periods in this period doubling sequence for which there is least evidence, especially directly in sunspot number series. But however, it is certain that this period exists in the phenomenology of the Sun, because it is now accepted that after 4 cycles there is a hemispheric swap. The leading hemisphere is swapped and the dominant hemisphere is swapped. There is thus a reset after 8 cycles. Apparently, there are some problems in the Sun after some of these hemispheric swaps. One instance is if you start with the epoch 1618 AD, which is minimum epoch in solar activity, and you add this period length of 45 years, you arrive at 1663 AD, right in the Maunder minimum. Possibly there is an occurrence of deep minima after such swaps if something fails. Is this the case now? This is a question today, because such a hemispheric swap was expected and indeed was performed at the 2008 minimum. As we all know, starting in the early 2000 years, there has been a deficiency in sunspots, in contrast at the solar surface and in polar fields. The second period for which the integral number of Schwabe cycles is a power of 4 is found around 168 years with a very large error bar of about 7%. It approaches 16 Schwabe cycles. There is some evidence in sunspot numbers, a large departure from the expected value of 176 years. And again, it seems that this maybe is a return period for deep minima. In the data of these authors, recent data of 2015, you can compute a median return period from the extrema in their series, and I found 168 year and 173 year. To the epoch that we just found in the previous page, 1663 AD, you subtract the period that we are now discussing, and you arrive at 1495 AD in the Spera minimum. Is this period also a return period for super maxima? There are some indications that this is the case. So this 16 Schwabe cycle periodicity would not be entirely detrimental, would not be an occasion only for excursions in solar behavior which amount to a deficiency, but would be a fluctuation that would be particularly sharp both in default and in excess. You see the examples here of adding the high maximum of 1614 AD to this period and arriving at the high maxima at the end of the 18th century. And from this end of the 18th century, the high maximum at the last epoch of a H Schwabe cycle pulsation plus this length, we arrive exactly at the historical highest maximum, which was in 1957. Then there is a special case, the case of the fluctuation found at nearly exactly 353 years, i.e. extremely close to the expected value from exact period doubling of 352 years. This is not a power of 4 and is also not a power of 8, 32. Maybe in the phenomenology of the Sun it corresponds to a return period for very deep minima. Here again from the data and two teams can be computed a return period, in this case now a mean value, and we find 358 years or 372 years. These are values that were estimated in this project that I assert they are not given by the respective authors. For instance, again, starting from the epoch computed earlier today, 1663 AD, we subtract the period of 353 years and we arrive close to the center of an earlier minimum, deep minimum, the Wolf minimum. More scary is the fact that if you now add this period, we arrive at the present time. Again, it is well known that the Sun has been since the late 1990s and in the early 2000s till present in a period of subdued activity. However, this 353-year period might also be a return period for super maxima. Here are these two examples of the 1614 super maximum plus this length. We arrive in 1967, the true epoch for the super maxima is, as said in the previous page, in fact 1957. And you see next super maxima would be at this date in more than 1 century. Now, if we turn to the lengths in this sequence of periods which correspond to multiples of the Schwabe cycles in which the integral factor is a power of 8, we find the 88-year period and the 707-year period. The 88-year period was determined from inspection of spectra in the literature and from citations of results in solar physics to be 88 years plus or minus only 2 years, i.e. From more than 85 years to less than 91 years. It is right on the dot at the expected theoretical period doubling length, and it is also very sharply defined. It is a period for which we have both considerable evidence in the amplitude in the sunspot record directly, and phenomenological backing for the rationale for such a strong fluctuation. The phenomenological support is from the phenomenon of the reset of a hemispheric lead after 8 cycles. And the amplitude evidence was described in my 2004 paper in the journal Solar Physics, the H-Faber cycle pulsation, in which I suggested 8 consecutive Faber cycles to compose such a pulsation from maximum epoch 1 to maximum epoch 8, and using the non-smoothed yearly mean maximum epoch for each cycle, we get for 8 cycles as a mean from the start of the relative sunspot number series in 1712 to the last 8th epoch in 1964. This list of amplitudes which are monotonously growing except at the 3rd slot. You see the epochs in the top line and the bottom line. So we have a factor 3, approximately 3, in the amplitude from the 1st epoch to the 8th epoch over an 88-year span. However, there are occasional disruptions in the record of such monotonous growth sequences in the amplitude of the sunspot number. In this presentation, you see that it takes place at the 3rd cycle. There is a drop after the 3rd cycle in the otherwise almost exponential monotonous growth of the sunspot number amplitude. You see, for instance, if you start from 1964 AD, which is a minimum epoch before the first maximum, and add 33 years, we find 1997 AD, at which epoch was first remarked that polar fields are weak, and which was preceding a weaker solar maximum in 2001. If we now look at the Maunder minimum, starting from the previous, from the minimum before the previous the previous maximum, which was in 1614, you add 33 years and arrive in 1651. Which is a realistic epoch for the onset of the actual Maunder minimum. If you add only 30 years, it is 1648, which is as realistic or maybe more realistic compared to actual sunspot data. 30 years correspond to the length of the poloidal cycle, which already introduced in a earlier video, and we'll discuss in detail in the next video. And you see, after the length of one poloidal 3 cycle of 30.1 years, we would have an interval of 57 years, which would correspond to a deep minimum, in this case the Maunder minimum, and the two add up to a 8 cycle pulsation in which the second part was failed. Perhaps we are now in such a situation with the current pulsation having started at the minimum of 1964. As for the longest detected period in this period doubling sequence, 707 years, it is also very much on the dot, as almost exactly 64 cycles. It is correspond to the square of 8 as the integral multiple. This was discovered as the previous one by Sonnet and Finney in 1990 and was confirmed by many other investigators, and the value that is suggested here, 707, is updated from the findings of Sonnet and Finney more than 2 decades ago. The phenomenology of this long period has yet to be explored. Maybe if it is not yet clear what it is, maybe in fact it has a rather weak effect on solar activity variations, although it has some effect. One question is whether this period is the longest in the sequence under review here. For instance, there is no detected period of 128 cycles, even though this length of about 1,400 years is well within the investigated time domain, in which we will separately find at least one fluctuation of more than 2,000 years. So perhaps in this this particular period doubling sequence, 707 years might be the longest one. If this was the case, it would confirm the hypothesis from theoretical physics, independently from any astrophysics or solar physics, that the physical phenomenon of period doubling, which is known in several other fields of physics, ends at 64 cycles or somewhat beyond. This was found in a couple of laboratory experiments, and maybe perhaps also the case for solar activity. It is now possible to suggest, to conclude that this sequence represents a set of toroidal solar oscillations because they are evident directly in the sunspot records, and the numbers of sunspots are results of amplification of the solar magnetic field in the toroidal region of the Sun. This is, so to say, a latitudinal solar cycle with winding up of magnetic field lines, as suggested in this work in the Fivefold Sun project in its first part, discussed in the first videos of this series of video lectures, while we will find separately and report in the next videos other sorts of other sequences in solar long-term oscillations which are not toroidal, which are poloidal or else, and thus will not be found so directly in the sunspot record. So because this sequence represents the final amplification in the toroidal area of the Sun of the variations in activity amplitude in the Sun, this sequence includes the periods with the largest modulation power for solar activity. At least this is what is strongly suggested as a result of this research. And within the sequence at hand today, the bulk of the modulation power is in the 88-year period, because it is the period in which we find a factor of as much as 3 for the amplitude over the length of the cycle, which is not a sinusoidal cycle at all, as the Schwabe cycle is not at all a sine. It is a sawtooth phenomenon. After sharp, almost monotonous, almost exponential rise from 1 to 3 in amplitude, there is a crash, and the phenomenon starts anew for another set of 8 cycles. Also, this period, which includes the bulk of the modulation power for solar activity, is known from a set of clearly detected epochs which is not the case for any period of longer length. Why is the 88-year cycle, including the bulk of the modulation power for solar activity, beyond the Schwabe cycle? The physical explanation seems to be straightforward. This cycle includes all the kinematic transformations of the solar ball, which are very simply defined, and which are the 4 polar reversals and the 2 hemispheric swaps. There are not any that are known. Maybe there are a longitudinal kinematic transformation. Maybe there are poloidal kinematic transformations. But what is known as of today and clearly accepted is what is stated here, and this is underpinning the 88-year cycle. Now there is perhaps a deeper root for this circumstance in mathematics and in the Fibonacci sequence, which, as we found in part 1 of the Fivefold Sun, as a book to be supporting the kinematic of the Schwabe cycle. Well, 8 in this sequence is the only cube. There is no higher power in the sequence. And in the Schwabe cycle itself, the number which is characteristic of the number of items, in this case of number of rigid rotations that compose the fluctuation, is 144 and is the only square in this Fibonacci sequence. Another conclusion of this research is that at the centennial scale there is no 70-year to 120-year variation band, as postulated in many recent publications, at least for any toroidal solar oscillation. In the toroidal sequence of oscillations, what is found is a very sharp 88 plus or minus 2-year oscillation. So if there is any 70-year or any 120-year oscillation in solar behavior, this is possible, but would be found separately, and indeed we will find at least one such other relevant sequence in another set of oscillations, and it will be no part of a continuous variation band because it is a completely different, separate oscillation. In the next video, we will introduce the sequence of poloidal oscillations. This is now the end of video 22. I thank you for your attention.